Okay, troops. Today we're doing conservation of angular momentum using this apparatus, a rotating turntable, a mystery mass, and a stop clock. That's pretty much it. Okay, and a ruler, because we might be measuring a radius. What we're going to do is we're going to set this turntable rotating and we're going to measure its angular velocity. And when it's rotating, we're going to drop a mass on it. This wee mass we're going to drop on it. And then we're going to see how it affects the angular velocity. Let's see how we go on. Excuse the noise. Okay, that bin there is now blowing air so that this turntable is free to rotate. And we're going to measure the time taken for 2 revolutions. Are we ready? And start. 1, 2. 3.01 seconds. Now we're going to drop the mass on it. There we go. And it has slowed down. We're going to time how long it takes for 1 revolution. So reset the clock. Go. Stop. 2.08 seconds for 1 revolution once the mass is on it. Now we're going to see if we can work out the mass of this mystery object. Okie dokie. I wonder what it will be. Right, now remember we studied linear momentum in higher physics. Momentum was mass times velocity, mass in kilograms, velocity in meters per second. So linear momentum was in kilogram meters per second. Angular momentum uses the rotational equivalent quantities, so moment of inertia times angular velocity. Remember, moment of inertia is mass times radius squared, so that's kilogram meter squared, times angular velocity, which is in radians per second. So your unit could be kilogram meter squared radians per second. Now, the same rules apply for angular momentum. Angular momentum is conserved in the absence of any external torques. So as long as there's no frictional torques or driving torques, then angular momentum is conserved. It's the same before and after a collision. So we're looking at conservation of angular momentum. We're going to use this apparatus. We've got a rotating turntable. The disc on this turntable has got a mass of 975 grams and a radius of 15 centimetres. That means its moment of inertia, which is a half mr squared, because it's a disc, solid disc, is 0.011 kilogram meter squared. And we are going to time how long it takes for 2 revolutions. That time on our stop clock was 3.01 seconds. So the angular velocity works out at 4.2 radians per second. 2 revolutions, so that's 2 times 2 pi divided by 3.01, 4.2 radians per second. That's the first angular velocity. Then we drop our mystery mass onto that rotating turntable. And the initial angular momentum of this dropped mass will be 0, because it's not moving in a circle. When we drop it onto the table though, it is now turning with the turntable, and the time for 1 rotation now is 2.08 seconds from our stop clock. So the omega now is 2 pi radians, 1 revolution, in 2.08 seconds, gives us 3.02 radians per second. Wrong unit there, my apologies, I've written seconds, should be a radians per second. Oops. 3.02 radians per second. Now, if we use our conservation of angular momentum relationship, I1 omega 1 equals, now we've got 2 masses, we've got the disc and, remember the disc's got a moment of inertia of 0.011 kilogram meter squared, but we've got the disc and the dropped mass moving afterwards. Now, the dropped mass was dropped at a distance of 13 centimetres from the centre, so its radius 0.13 metres. And that dropped mass can be considered a point mass. All the mass is concentrated at a distance of 13 centimetres from the centre. So if we sub in all the information that we have into this relationship, now bear in mind that both the disk and the dropped mass both have the same angular velocity after the mass has been dropped. They're both turning at the same rate. So let's sub all these numbers in. So the disk's moment of inertia, there it was away up there, times its angular velocity, 4.2, is equal to the disk's moment of inertia plus the dropped mass's moment of inertia times our second angular velocity, 3.02 radians per second. We've got one unknown, that's I2, so we can rearrange all this and try and find the moment of inertia of the dropped mass. So it's going to be the left hand side there divided by 3.02 gives us the 0.011 plus I2, and then subtracting the 0.011 gives us I2 on its own. And if you do that calculation, we get 0.0043 kilogram metre squared. Now, that's the moment of inertia of the falling mass, a point mass, once it is on the turntable and rotating with the disc. Now, it was dropped onto the turntable at a distance of 13 centimetres from the centre and is considered a point mass. So, the relationship for the moment of inertia of a point mass is mr squared. We can sub in for that moment of inertia, 0.0043, and the radius was 13 centimetres. That means we could work out what the theoretical mass of that mystery object was. So rearranging for m, so m is the moment of inertia divided by the radius squared is, drum roll please, 0.25 kilograms. Now here's our mystery mass. Here it is. It's 450 gram masses and a 50 gram mass carrier. It's 250 grams. Bingo. Here you go. 1, 2, 3, 4. 450 gram masses and a 50 gram mass carrier. 250 grams. That's magic.